Now, in this screencast, we're going to learn how to use Newton's method for a system of nonlinear equations. Remember, in a previous part of this lecture, Lecture 6, we had learned Newton's method for solving a single nonlinear equation. But in this case, we're going to expand on that idea. So if you have a system of two or more nonlinear equations to solve, we have to do this expansion to take that into account. So consider this 2 by 2 system where you have f as a function of x and y, and g as a function of x and y, and you want to find the x and y where both of those equations are equal to 0. So to find these zeros of the system, we have to find these values of x and y that satisfy those equations. So remember, we had previously considered a set of nonlinear equations from page 2 of the same lecture, shown here. And so the question is, in this example, can we find the x and y values that are the 0 of this system? So remember, in one dimension, to derive the algorithm for Newton's method, we had to Taylor expand the single function that we were trying to find the 0 of. In this case, we have two functions that we're trying to find the 0 of, so we have to Taylor expand in 2 dimensions. So in this case, what we're doing is we're going to expand about xi and yi, this point, which is the ith iteration of our attempt to solve for the 0 of this system of equations. And we want to approximate f and g at xi plus 1, yi plus 1. So that's what we're going to do. We're going to do this Taylor expansion. And just for convenience, so I don't have to keep writing this ordered pair here, we're going to let the subscript I mean that we're going to evaluate at that ordered pair. So this is what it's going to look like when we Taylor expand. So we have f evaluated at xi plus 1, yi plus 1 is approximately equal to f evaluated at xi, yi plus, now remember, in a Taylor expansion in one variable, this is going to be a first derivative term. So that's what we're going to have here, except for since it's in two variables, it will be a partial derivative. So the partial derivative of f with respect to x evaluated at xi, yi times xi plus 1 minus xi. Now, since there are two variables, we have to do this for both variables. And so you have another term that's also a first derivative term. So you have plus the partial of f with respect to y now, evaluated at xi, yi, times yi plus 1 minus yi. Similarly, we can Taylor expand g of x and y. So g evaluated at xi, yi is xi plus 1, yi plus 1, sorry, is approximately equal to g evaluated at xi, yi plus the partial of g with respect to x evaluated at I times the distance between xi plus 1 minus xi plus the partial of g with respect to y evaluated at xi, yi times yi plus 1 minus yi. Now before we go any further, note that this is something that I'm going to call delta x. This is something that I'm going to call delta y. Another thing to note about this system is that all of these derivatives, so for example, the partial of f with respect to x evaluated at y, and all other first derivatives these are all just constants. And the reason why they're constants is because we are evaluating them at xi and yi. So for convenience, we're going to call them a1, a2, a3, and a4. And I found what this does is it sort of takes the mystery out of this, so we don't have to look at a whole bunch of partial derivatives. All we're looking at are a whole bunch of constants. Okay, so as before, with the Newton's method in one dimension, we're going to find where our linear Taylor series approximation gives us a 0. So this is the best possible guess that we can make. So we're going to assume that fi plus 1 and gi plus 1 are equal to 0, and we're going to solve for delta xi and delta yi. So the way this equation now shapes up to look like is 0 is equal to f evaluated at xi yi plus a1 delta xi plus a2 delta yi, and also the other equation 0 equals gi plus a3 delta xi plus a4 delta yi. Of course, this gives us just a 2 by 2 linear system to solve, and we can go ahead and solve this system kind of by putting it in matrix form first. So if we put it into matrix form, what we get is, and let me just make sure that we can scroll back up so we can look at both things at the same time. What we get in matrix form is the matrix here, A1, A2, A3, A4, times a vector of unknowns, delta xi, delta yi, is equal to, and what I'm going to do is I'm going to move fi and gi over to the other side of the equation, so this is minus fi and minus gi. Now, for convenience, what I'm going to do is I'm going to call this matrix, I'm going to call it ji. I'm going to call this delta capital X sub I. I'm going to call this minus fi. Now this is a vector, and this is also a vector, and this one here, ji, is a matrix. So another way to see this is delta xi is equal to minus ji inverse fi, where these two are vectors. Fi and delta xi are both vectors, and j is your matrix. So this is why we learned how to solve a system of linear equations, because when you use Newton's method in 2 dimensions, you have to solve a system of linear equations at each step. Now, just to put this all in context, you may have heard of this before, but our matrix J here is something called the Jacobian matrix. But all it is a matrix full of first partial derivatives. So J in general is going to look like the partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y, all evaluated at xi, yi. And then you have your matrix here that you can then take the inverse of and then find your delta xi at each step. Now, to wrap this all up, let's go ahead and compare this to Newton's method in 1 dimension. So Newton's method in 1 dimension, recall, was xi plus 1 equals xi minus f of xi over f prime of xi. Or we could have also written that as delta xi is equal to minus f prime of xi inverse times f of xi. So you see that there is a direct analogy here between the 1 dimension and the 2 dimensions. And of course we can then, after that, we can expand this to n dimensions. So if my f here, vector of f, were instead of just f and g, we had f1, f2, dot, 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 all the way down to fn. That was my vector for f. If my vector for x instead was, or sorry, delta x, instead of just delta x I and delta yi, if I had delta x1, sorry, delta x1i, delta x2i, delta x3i, dot, 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 all the way down to delta xn evaluated at I. And if I were evaluating this system f as a function of x equals 0, so this is an n by n system, then what I could get in the end is that my Jacobian matrix, just as long as I can find my Jacobian matrix, which is just a whole series of derivatives, partial of f1 with respect to x1, partial of f2 with respect to x2, dot, 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 partial of f1, oops, let me go back, this is not partial of f2, sorry, this should still be partial of f1 right here with respect to x2, and all the way over to partial f1 with respect to xn, partial of f2 with respect to x1, partial of f2 with respect to x2, dot, 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 partial of f2 with respect to xn, and of course the final row will be partial of fn with respect to xn, x1, partial of fn with respect to x2, dot, 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 partial of fn with respect to xn. So we can fill up our whole Jacobian matrix this way. Then in the end we have delta xi is equal to minus ji inverse fi in the exact same way we had before, except for now we just have an n by n system instead of just a 2 by 2 system.